In the last class, we looked at the nature of electromagnetic waves, and we saw that every electromagnetic wave is essentially made up of an electric field component and a magnetic field component, which are time varying. The other thing that we noticed was that the nature of the fields is such that the electric field is orthogonal to the magnetic field, and both of these are orthogonal to the direction of propagation of the wave. So, as a special case, we looked at the electric field existing along the x-axis or varying along the x-axis, the magnetic field varying along the y-axis, while the propagation of the wave is along the z-axis. So essentially, what we saw was in a homogeneous unbounded medium which is a perfect insulator. We saw that as a special case, the electric field, let us say, exists along the x-axis. So that's why we called that field as Ex, and its magnitude sort of varies in this format. So as you can see, this is very similar to the voltage solution on a transmission line, where the wave is essentially traveling along the z direction. This first component indicates the wave traveling along the plus z direction, and this indicates the wave traveling along the minus z direction. So in some sense, this is the backward wave or the reflected wave, and this is the incident wave. But if the medium is unbounded in general, then the second wave need not even exist, because there is nothing from which the wave will be reflected. So likewise, the magnetic field or the H field which exists along the y-axis, its nature is something like this, which is very similar to the current along the transmission line. So this eta is the intrinsic impedance. Intrinsic impedance of what? Of the medium. Which we saw is defined something like this: the root of mu by epsilon of the medium. We also saw that in general, this was a special case of the fields existing along the x and y axis respectively. We also discussed that in general that need not be the case. The electric field vector, the magnetic field vector in general can exist on any plane which are perpendicular to each other in the directions, and which in turn are perpendicular to the direction of propagation of the wave. So we said that in general, if the electric field vector is existing along any plane rather than along an axis, we can actually look at the locus of the electric field vector tip, the way it changes with time, and essentially we saw that is called as polarization. So polarization is nothing but the way the electric field vector tip changes its position as a function of time. So in general, we saw that when we look at polarization, the most common form is an ellipse. So we can say that, let us say, if these are the axis and if this is the x-axis and this is the y-axis, the electric field vector, if it exists on the xy plane, and if you assume that the wave is traveling along the z direction, so let's call this as z. So in general, we can have the electric field vector trace out this kind of a locus. So this is the elliptical case is the most general because all possible cases are covered by this ellipse. So we saw that when the phase difference between the electric field x and y components is 0, as a special case, this ellipse becomes a straight line. So in that case, the ellipse would, or the electric field vector would oscillate along this axis. So that is one special case. The other case we saw was that when there is a phase difference of pi by 2 between the electric field components along the x and y directions, then this ellipse essentially turns into a circle. So we saw that in general the circle could be such that the electric field vector rotates either clockwise or anti-clockwise, which we called as the left hand circular polarization or the right hand circular polarization. Likewise, even for the ellipse, there will be some kind of a rotation. So if the ellipse rotates, or rather the electric field vector tip rotates clockwise along the ellipse, then we will call it as a left hand circular polarization. And if it rotates anti-clockwise, we will call it as a right hand circular polarization. So in general, elliptical is the case. So we can say that every wave in general is elliptically polarized. So that ellipse could be a straight line, it could be a circle, that comes later. So in general, you can take a look at this ellipse, and just like how we define for conic sections, we can define the major axis as some A, and the minor axis we can define it as B. Now we define that the angle which the major axis makes with the x-axis, we can call that as some angle, let's say tau, where the ratio A and A by B is essentially called as the axial ratio of the ellipse, and the angle tau is called as the tilt angle, how much the ellipse is tilted with respect to the x-axis. So in general, the axial ratio or AR can vary between 1 to infinity. So AR becomes 1 for circular polarization, and AR becomes equal to infinity for, when would that become infinity? When the B would become 0. So it is for linear polarization. So in general, there was a French mathematician called Henri Poincare who did a lot of analysis of these mathematics behind the polarization, and essentially came up with a solution where you could represent any state of polarization using a single diagram. So let's see what that is. So now we had defined for an ellipse there are two quantities, axial ratio AR and tilt angle tau. Now even though axial ratio is defined as A by B, we can say that this is always positive. But the mathematician Poincare, he said that let us make a very small change. Let us define a sign convention for the axial ratio. So if axial ratio is negative, then we will call it as right hand polarization. And if axial ratio is positive, we will call it as the left hand polarization. Of course, when AR becomes 0, at that time you get a linear polarization. So for that, talking of right hand or left hand, there is not much meaning. So Poincare said that you can represent the all possible states of polarization in the form of a sphere. And it is not just any sphere. It is the sphere which is very similar to a globe. Now, as you know, in geography, globe is nothing but the 3D representation of the surface of the earth. So what you see is a globe is nothing but a grid consisting of horizontal lines as well as vertical lines. So the horizontal lines are called as the latitudes and the vertical lines are called as the longitudes. So Poincare, he essentially did something of this kind. He said, take a globe and let us say this is the equator of the globe. So the latitudes can be drawn this way. And the longitudes can be drawn connecting the north and the south poles. Something of this kind. So this is the 0 degree latitude, which is also the equator. This is the north pole and this is the south pole. So Poincare said that the north pole corresponds to a circle and the south pole also corresponds to a circle. But the north pole denotes the left hand circular polarization and the south pole denotes the right hand circular polarization. So all possible circular polarizations will be at these 2 points. Why 2 unique points? Because for circle, if the polarization becomes a circle, the axial ratio becomes 1. And the tilt angle, you can take it as either 0 or pi. So therefore, if we were to represent this using the axial ratio and the tilt angle tau, they will map onto the north and the south pole because the tau essentially becomes 0 or pi at these 2 points and the axial ratio is 1. So essentially the axial ratio denotes how far away you are from the equator. So closer you are to the equator, the axial ratio will go far and far away from 1. So that is the convention which he had used. Now along the 0 degree latitude or the equator, now Poincare said that as you move along this 0 degree circular periphery along the equator, you will see that this line essentially indicates all possible states of linear polarization. Why linear? Because for linear, the axial ratio becomes infinity. It could be like this, but the tilt angle tau can change. It could be like this, anywhere. So while axial ratio is fixed to infinity, that is why you are fixed on the latitude, but since the tilt angle can change, your longitude essentially changes. So axial ratio tells you how far away you are from the equator, and the tilt angle essentially corresponds to the longitude. So somewhere it will be like this, somewhere it will be like this, like this, like this. So different states of linear polarization. And all the latitudes between the equator and the north pole will represent left hand elliptical polarization, and all the latitudes between the equator and the south pole would represent right hand elliptical polarization. So we have defined AR with a sign convention that negative means right hand polarized and positive means left hand. So if you are going further north from the equator, you will get left hand polarized. If you go south from the equator, you will get a right hand polarized. So that is how Poincare had represented this in the form of a ellipse, or in the form of a globe, all the possible states of polarization. Now having established some of the basics of electromagnetic waves, we saw what is the simplest possible case where we solved the Maxwell's equations for a homogeneous unbounded medium, and then we saw that we get field relations something like this. So what we saw was, in a perfect dielectric, the propagation constant gamma square is nothing but minus omega square mu e. This is the propagation constant. So propagation constant, as you know, gamma is alpha plus j beta. So when we look at this gamma, it is nothing but minus j omega under root mu epsilon. So as you can see, gamma is purely imaginary, or rather I should not use the minus sign over here, it should be plus, because the minus will be absorbed by the j. So this is nothing but j beta. So in the perfect dielectric, you have the propagation constant as a purely imaginary quantity. So that is like saying the alpha is 0. So perfect dielectric kind of behaves like a lossless transmission line. But when we are talking of media, we need not always have dielectrics. As you know, we can have medium with conductivity also. We can have conductors which are very, very good, or conductors which are not that good, but they still have some non-zero finite conductivity. So therefore, conducting media sort of behave like lossy lines. Where alpha need not be equal to 0. So now the question is, how can we represent conducting media? For conducting media, the distinguishing feature is the sigma will not be equal to 0, the conductivity. So in case of perfect dielectrics, we had said that let the medium be such that there are no free charges. So therefore the conductivity is always 0 in the dielectric. What exists is the displacement current. So in case of conducting medium, how would the Maxwell's equations change? So the Maxwell's equations will change only for the Ampere's law. So in case of dielectric, we had taken Ampere's law, the curl of the magnetic field is nothing but the displacement current density, because there is no conduction current density. So now what will happen is Ampere's law will change into something like this, its normal form. So what will now happen? We can actually write the J and D as functions of electric field. So this is nothing but sigma times electric field. We are still assuming that the medium is isotropic. So, and you know that D is nothing but epsilon times E. And we know that if the fields are time varying, which they are for any wave, the time differential can be represented as a j omega operator. So therefore I can say this is nothing but j omega epsilon E. Now in general, we know that the epsilon or the permittivity of a medium is nothing but the relative permittivity multiplied by the permittivity of free space. So therefore I can write this as sigma E plus j omega epsilon r epsilon 0 times E. So what we can now do is we can take this j omega epsilon 0 common. So what we will get, if we take this from here, we will get epsilon r, the second term I am writing first, and when you divide j omega epsilon to the first term, it becomes a negative term as the j goes to the numerator, sigma divided by omega epsilon naught times the field vector. So now this is what it looks like. Now compare this with respect to the perfect dielectric, where this was something of this kind, j omega epsilon 0 times epsilon r times E. So if you take the j omega epsilon 0 common, what you only have is the epsilon r over here and even E separated, which is over here. So what you see is the effective permittivity of the medium sort of changes. In case of the dielectric, epsilon r was the only measure for the dielectric property. However, the dielectric constant for a medium having some conducting component essentially becomes something like this. So what we can say that in such a case, the effective permittivity of the medium, or epsilon effective, that is nothing but what? Epsilon r minus j sigma divided by omega epsilon 0. So now what you are seeing is the permittivity is no longer a real value. It is some complex value depending on what is the conductivity. So now what we see is that since the epsilon is becoming a complex quantity, we must ask ourselves, what are the conditions for which the medium behaves more like a dielectric, and what are the conditions for which the medium behaves more like a conductor. So since the medium has now properties of both dielectric as well as conductor, so one might definitely ask that which one prevails. Of course, it depends on all these quantities. So what we can say is that when the imaginary term becomes very, very large, the medium behaves more like a conductor. So I can say when sigma becomes much, much more than omega epsilon 0, the medium behaves like a conductor, or I should say behaves more like a conductor. And when sigma is much, much less than omega epsilon 0, the medium behaves more like an insulator. So when you have a medium, the epsilon r is fixed and the sigma of the medium is also fixed. Epsilon 0 is already fixed. What changes is the frequency. So now what is surprising is, by changing the frequency of the waves traveling in the medium, or the frequency with the way the fields exist in the medium, we can say that at certain frequencies the medium will behave more like a conductor. At certain frequencies the medium will behave more like an insulator. So now this is something which is very, very interesting, and this happens with many kind of media. For example, seawater. For certain frequencies it behaves like an insulator. For certain frequencies it behaves like a conductor. So now we can define a quantity called as the transition frequency or the transition angular frequency, that is omega t. So that we can define in the following way: sigma divided by epsilon r epsilon 0. You can simply rearrange the terms and get this. We define the transition frequency as that frequency at which the real and imaginary parts of the epsilon become equal. So now we can say that if the angular frequency, or let us define the transition frequency, so that means ft is nothing but 2 pi, this factor will come. So I can say if the frequency of operation of the signal inside the medium is more than ft, then what? If the frequency becomes very, very high, this term will become very, very low. It will behave like a good dielectric. And when f is much, much less than ft, this will behave like a good conductor. So now, since we defined the epsilon effective as a complex quantity, we can now go back and write the propagation constant gamma by incorporating the complex permittivity. So we prove that for any medium, the gamma square is nothing but omega square mu epsilon. So now epsilon is a complex quantity. So therefore we cannot say that it is a lossless medium. So what we can say now is it is omega square mu will not change, epsilon 0, epsilon r, or what we should say actually epsilon effective. So substituting what we have got over here into this equation, we get minus omega square mu epsilon 0 So this is what it looks like. So then I can say gamma will be nothing but the square root of this, which is nothing but j omega under root mu epsilon 0 this raised to half. So I am taking the root of the entire expression. So what we can see from here is that if sigma becomes very low, this term essentially disappears, and then the quantity inside the bracket becomes only root of epsilon r, and then this approaches j beta. So if sigma tends to 0, then gamma will tend to j omega times the mu epsilon, which is nothing but j beta. So therefore this sigma has a direct effect on the alpha. So alpha meaning the attenuation constant when we are correlating with the transmission line. So what happens is when sigma becomes very large, this will be a complex number in general, and then you have to find out the square root of this complex quantity, and then you will get gamma as some alpha plus j beta. So just like the case of transmission line, you can make alpha as 0, but beta you can never make as 0, because beta is the property of the frequency as well as the property of the medium. Now let us take the ratio of the conduction current to the displacement current. In the medium. So what is that? So we had seen this is the indication of the conduction current, and this is the indication of the displacement current. So this ratio would be the imaginary term divided by the real term. So that is nothing but sigma divided by omega epsilon 0 epsilon r. Now this quantity has a very special name. This is called as tan delta. Why tan delta? Is because this delta denotes the phase angle of the complex effective permittivity of the medium. So delta is the phase angle of the complex epsilon effective, and this quantity is called as the loss tangent. So whenever you come across the data sheet of any medium which you are going to work with, they all have a specification of their loss tangent or the tan delta. So lower the sigma, lower will be the tan delta, and better is the dielectric property. So let's say, for example, there are many dielectrics which are used in practice for making transmission lines or any medium for guiding electromagnetic waves. Now, one of the simplest examples of a dielectric is something that is used to make printed circuit boards or PCBs. So PCBs or the printed circuit boards, they are made of a compound called as a glass epoxy compound. Which is supposed to be a dielectric. The material is also called as FR4. FR stands for flame resistance grade 4. So generally the epsilon R of that medium is about 4.3 or 4.4, something like that. So at some frequency, let us say they'll mention, let us say at 1 gigahertz, the tan delta is actually 0.02. Now tan delta is what? Sigma divided by omega epsilon 0 epsilon r. So now you know that at 1 gigahertz the tan delta is very, very small. That means even the conductivity is very, very small. So it's a fairly good insulator. But if you want even better material, you can go for something called as PTFE, which is a Teflon compound. So where tan delta is of the order of 0.001, which is 20 times less than that of FR4, and this has epsilon R of roughly about 2.2. So what you see is, when I am plotting the loss tangent or the tan delta as a function of omega, what I see is the loss tangent can be very, very high at low frequencies, because omega becomes less, means this whole quantity increases. For a given medium, sigma, epsilon, these are all constants. What changes is omega. So therefore the behavior is something of this kind. So it's kind of like the two axes are acting as asymptotes for this curve. This is what it looks like. So now for a medium, with non-zero sigma, a medium with non-zero sigma, what will be the intrinsic impedance eta? You can very easily prove that in such a case, this eta will be a complex number, just like how a lossy transmission line has a complex Z0. You can prove that this is nothing but j omega mu divided by sigma plus j omega epsilon. I encourage you to try this out as a proof. It is a very simple proof. So where obviously mu is nothing but mu r times mu 0 and epsilon is epsilon r times epsilon 0. So let us now take another quick look at the gamma. So what we had written was, for the conducting medium, the gamma square is nothing but minus omega square mu epsilon 0 epsilon r minus j sigma divided by omega epsilon 0. So we can actually rewrite this by opening the bracket, and what we will get is minus omega square mu epsilon 0 epsilon r plus this epsilon will cancel out and even the omega will become the power of 1. So we will get j omega mu sigma. So what we are seeing now, this gamma term becomes this complex quantity, the gamma square rather, and if I now take j omega mu common, what I will get is sigma plus j, even I can take a j common here because omega and mu are both here. I can take a j common out here and that would become minus 1 by j, so which is again a j. So this will be j omega epsilon 0 epsilon r. Now let us suppose that the medium is a very good conductor. So suppose gamma is much more than omega epsilon 0, this term. Now what will happen? If gamma becomes, the sigma becomes very high as compared to this omega epsilon 0, what will happen is inside the bracket the real term will start to dominate and the imaginary component will start becoming negligible. So that means gamma square now will rather tend to j omega mu sigma. So that means the gamma is nothing but root of this quantity, whatever it is. So we shall pause here for the time being and continue from this point onwards in the next class.